R. This is a viscous liquid. Read the question and get into the all these are some good geometry based, so where you're supposed to make observation of the diagram. Where the disk is in contact, the lower part of the disk is in contact, no, the lower surface and upper surface. This is the lower surface, this is the upper surface. This is the viscous liquid till here. Neglect the edge effects. The end effects are to be neglected. What do you mean by the end effects? These things here, because the liquid is in contact with this side walls, so these end effects are to be neglected. Only consider the effect of viscosity on the bottom of the disk, bottom surface of the disk. Top surface, there's no liquid, so no question of that one. So as you rotate, the viscous drag will oppose relative motion. Okay, let's directly get into the there's a disk of radius r. I'm going to assume a strip. Okay, this one, so let me assume a strip. So let the radius of the strip, let it be small r. The disk is having angular velocity omega. How the tangential velocity of this point should be like this, and what is v equal to? V equal to r omega. Proceed like this. Have this much of information. Okay, let's get into this one. Where the viscous drag will act, viscous drag will oppose relative motion. So it will act at all points on the ring. So let the force acting on, let it be df, that one. So there's a disk. On the disk at the bottom, I'm assuming a ring of radius r, thickness dr. Now what is the area of this one? So let's calculate the viscous force acting on the ring. Viscous drag on the strip, on the circular strip. How much it should be? df equal to eta dA into V by H. Try to follow this. Sir, where is H? H is this one, no? You take any part of the strip, at what distance it will be from the bottom reference, that one, at a distance H. What is V? Tangential velocity, because it's rotating, all points will have same speed. What is dA? Area of the strip. Anybody? dA? 2 pi r dr. What is V? V is r omega by H. So this everything will become 2 pi eta omega H will come as it is. So r square dr. Okay, this is the force. Already such a thing you have come across where in the torque concept in moment of inertia in the rotation mechanics. A disk is spinned on rough surface and released, then time taken by to come to rest. The similar there, the friction came, here the viscous drag. Now what about the torque on this one? Torque on the circular strip. What will be the torque on the circular strip? D tau equal to df into r. What is df? 2 pi eta omega h r dr into r square r cube into what should be the limit? 0 to capital R. So what is the total torque? Pi eta omega r to power of 4 by 2h is asking power. Okay, this much of external power is what I should apply on the disk, which is given an angle, so that it will rotate with that constant angular velocity. I think many spinning instruments will be there, if you go for industry or even in home everywhere. So these are the things what we needed. Slowly getting the idea. This one, different types of rigid bodies will be rotating. What should be the disk? It should be rigid. If it is a elastic body, anything will happen. The radius will change. Then no longer we can't write this one. No. So therefore, the disk should be a rigid one. Now I'll scroll down.